Hello, hello. Welcome. It's been a long time. I got some screen over here. I got some screen over there. I got my folding phone. Let's see if anyone still watches this stream. Let's see. Where have I been? I don't even know. I haven't been streaming. That's true. But in some ways, I think the meta of the George Hotz character is played out. I think we're entering a new era. I think the pendulum is swinging backwards. The pendulum is swinging back. So, yeah, I think... I don't know. I don't really know what this stream should be. You can see I'm in a new place. This is my office. It's a shared office, but we're here and we're streaming, and it's Sunday. Mostly what I want to do is show off some of the stuff in tinygrad, and then maybe we could do some work on it. So tons of progress has been made in tinygrad. Yeah, I mean, a lot of commits. I don't really know what to show you. I mean, there's beautiful MNIST. Beautiful MNIST is pretty nice. But it's the same beautiful MNIST that was there before. Actually, the accuracy is a bit higher now because we improved the initialization. If we go in here to NN and init, you can see that our initialization is simpler now. When you look at conv2d, it's really just tensor uniform and scale. You used to have k-ming uniform, but I don't really know what k-ming uniform is. Like, if you asked me to just describe k-ming uniform, but this is what Torch uses, so we just copied Torch, and now our kernels are a little bit more accurate, which is cool. tinygrad has docs. If you haven't seen them, I saw some guy on Twitter liked how much meth there was in the docs. I see all the meth. This is, yeah. I don't know. I mean, maybe we should try to implement a paper. I think that might be more fun. I don't know how far we'll get though. The new tutorial is helpful. Which tutorial? Well, we have the quick start and we have the MNIST tutorial. The MNIST tutorial is pretty nice. Oh, let's see. I went to Poland. Where are you so long? I went to Poland. Where else did I go? I went to Italy. I went to a lot of places. And it's cool because, tinygrad's it's a remote company. One of the ways that we distinguish ourselves from comma is we do have some stuff in the comma office, but tinygrad fundamentally is a remote company. 2 of our employees are fully remote because fundamentally it's a GitHub and a Discord. If you haven't seen our beautiful GitHub, it's GitHub tinygrad. We have a lot of stars. Yeah, I think what is tinygrad for? I mean, it's going to replace PyTorch, probably. We'll see. Now, look, something I say about this a lot is when I was in the self-driving car space, I was competing against largely idiots. Sorry, everyone who worked on self-driving cars, you were mostly like an idiot. And no respect. Whereas the people who I compete against here, like PyTorch, Jax, Mojo, MLX. These are people who are very smart and people I respect. So we're playing in a real playing field now, right? Do I respect the ADAS engineers at Toyota? No offense, but no, you're not good. Oh man, we had a Ford engineer come over and we showed him the docs and he's like, wait, that's the same docs we have. I'm like, yeah, anyone can go to techinfo.ford.com and buy them, right? They're just not, they're not on the kind of Pareto frontier of of coding, right? Like the reason the Toyota ADAS sucks has nothing to do with like that we're better engineers than them or anything. It's not even that. It's like structurally broken. Where there's nothing at all structurally broken about PyTorch or JAX. All right, like PyTorch and JAX they've made different trade-offs from tinygrad, and it's a question of who's going to win. But think about it more like high-level sports teams competing, right? Like, you can talk shit about the other team, but fundamentally, they're live players. Whereas OpenPilot's competition, except for Tesla, which isn't really our competition, we're not live players. Tesla and I don't share. Tesla and OpenPilot don't share much market. It's iPhone and Android. But we are trying to, of course, take all of the market share from PyTorch, JAX, and every machine learning library. So yeah, if you, let's see. I rafted down the Colorado River. Oh man, it was 115 degrees outside. It was cool. It was not cool. It was very hot, but it was fun. Hello, we're streaming. Hello. Yeah, well, so this is a shared office. You can say hi if you want. This is Chen Yu.
Hello.
He works at TinyCorp. Yeah, we gotta make MCTS fast. 500 nodes per second.
Which platform?
All of them. All of them. Tinybox definitely, yeah. Well, I can at least parallel the rendering and the. I don't know what percent of the time is spent on the rendering versus spent on the actual compilation. So what we're discussing here is I just added MCTS search. So if I put in beam numbers that are greater than 100, it doesn't actually use beam search. It uses MCTS search. So what this is doing is searching over tons and tons and tons of kernels. You see it found the best one there at 63. But this is a more high-level tutorial. Let's, okay. I don't know why I read the comments. What do you mean? Nvidia will go open source. Nvidia's always been open source. Not always, but for the last 2 years, they've had an open source driver. And they are switching now to solely the open source driver. Their closed source driver didn't use the GSP. It's just like, who am I even talking to? I'm the AMD thing is, the amount of just complete misunderstandings and Wow, I thought we weren't gonna rant. I thought we're past this on stream, but okay, scale, CUDA, AMD, right? So this stuff comes out and people are really excited about this. Look, there's still this is totally the wrong approach. There's no reason anyone should be doing this. Fundamentally, the question is not can you run CUDA, but the question is can you run CUDA fast? And the answer is you never will be able to. And I can show you why. I can show you. I heard there were some docs that address this, but I'll tell you why it'll never be good. So here, tinygrad supports both AMD and Nvidia, and I can show you here in where is it? It's in lowerer. It's not in lowerer. It's in kernel. Yeah, it's here. Yeah, here. So AMD and CUDA have very different tensor cores. I should probably include the comment for the AMD ones. So AMD and CUDA have different tensor cores, and because of this, they will never, you'll never be able to take CUDA code and compile it and make it fast on AMD. So this is not like, this isn't really going to help people the way they think it's going to help people. You want to be at a level of abstraction higher than this. You want to be at a level of abstraction where, like, you can still mess with your shapes such that it can make the tensor cores fast. So yeah, this will never be fast. This is the wrong approach. Now we'll give a shout out to TensTorrent. TensTorrent, I love to see this. They're shipping computers, right? Like, respect. Right? There's a button here. There's a deposit. They have a ship time. Oh, we're shipping tiny boxes too. I guess there's I don't even know what to like say about this. I got a room full of tiny boxes over there. I think we've shipped like 25 of them. They're shipping. We are very slowly making our way through the huge pre-order list. And if you want to, of course, add yourself to that, it's on tinygrad.org. Just click tinybox. These are the tiny boxes we're selling. Like, we can peek around a tiny box here. See if anyone's on this one. This is a tiny box green. It has 6 4090s in it. Just kick off a an MCTS search here. Let's just do something like this. Just why not? Let it search. Make sure it works. I haven't really tested it there. So MCTS is still very experimental. It's in extra. Yeah, but this is the tiny box. What's the ratio of what people are ordering? What do you think? Okay, it's 10 to 1, and you can decide which direction it goes, despite saving $10,000. But, we are almost ready to upgrade this driver quality from mediocre to acceptable, because, again, with no help from AMD, we've completely succeeded. Shout out to Nimmelgen, did most of this work. He works at TinyCorp. You can find him on our Discord. This is a complete AMD driver. It uses PM4. So a lot of the bugs in AMD basically existed in two places. One of them has to do with this feature called CWSR, Compute Wave Save Restore, which is basically like context switching for the waves implemented on the CPU. GPUs do kind of a quick context switching for the waves, but this slow context switching, 1 in 100 times, 1 in 1,000 times in a restore, it just wouldn't work. There were some race conditions in that. So we disabled that in the driver. It's just a flag you can use to disable it in the driver. And then we wrote our own. This is an AMD driver that speaks directly with the hardware using I/O controls. And the key thing is that we communicate with it through PM4 packets, not through AQL. So the other bugs existed in AQL mostly. Remember all those ones about, we're like the queue, they were messing with in order and out of order. Remember that thing they released? All stupid. We just bypassed all of it. So the main firmware that actually runs these things on the GPU. Oh, we have some decent docs now. Again, why wait for AMD to do anything? I just went in there, I used to be a famous reverse engineer, and we just dove in and said, okay, so what's actually going on here? So this is the main controller, the micro engine compute that actually controls like using the compute resources of the GPU. So it's a 250K binary. 90% of that code deals with AQL. But there's a lower level thing called PM4. So you can see PM4 instead of AQL. It used to be called KFD. Now it's just called AMD. We switched from AQL to PM4, which these are actually just speaking like this is the launch of a compute kernel here. You see we have a function called exec here. This specifies like the, just the location of the program, a bunch of different resources that the program needs. The local size. Where's global size? Oh, this is in this pointer to dispatch packet. Wait, what? didn't know this was still used. Huh. Interesting. I haven't read this code that much. Pointer to dispatch packet. Why do I need a dispatch packet? Why am I not just putting this stuff directly? I am putting it directly in. We're doing direct dispatch. Why is this stuff still in here? Pointer to dispatch packet. Get command IDX. Oh, maybe it's just a useful struct to use because this doesn't actually seem like it's doing anything. I'm going to ask about this in Discord. Oh, wait, what? Kernargs, pointer dispatch. I'm going to ask about this in Discord. Why is HSA kernel dispatch packet still used in ops AMD.py? Yeah, okay. I would imagine we actually didn't need this HSA thing because we're not really using it. So you can see these set SH registers. These are actually setting hardware registers in the GPU. And you can see here's where we set up the local size, and here's where we set up the global size. So this is just completely like specifying to the registers, like it doesn't even use the firmware. The MEC is executing very small pieces of code to actually run these register sets, and they're pretty much just exactly what you think they are. There is still this packet3 dispatch direct, so these are the different PM4 commands. Yeah, but turns out that when you bypass all of AMD's crap, there aren't really bugs in it anymore. So there aren't really bugs in the hardware. It seems like they did a good job with the hardware. It seems like their bugs exist in the driver and in their runtime. So we turned off the one buggy feature of the driver, and we bypassed their runtime entirely. So yeah. AMD, so we can upgrade this driver quality from mediocre to acceptable. I think should we do that? Should we upgrade it from mediocre to acceptable? I'll do it later. Okay. So we also have the same driver for Nvidia. This is the Nvidia version of that driver. It speaks directly to the GPU. It's amazing how short these things end up being. So one of the next big things that we're pushing into is we're still actually using the compilers here. So we're using NVRTC, which is it's an in-process CUDA compiler. Some weird stuff for PTX here. That's actually not on my computer. The same thing for the AMD compiler. We have a helper here that calls compile hip. Which I don't really know why that's not in ops AMD. That should probably be moved to ops AMD. Because we don't use the same compiler here. Why is this a separate file? That probably belongs in ops AMD. I'll mention this in Discord too. Reason we can't put merge hip co-manager.py into ops AMD.py. Then elf.py can go to helpers.py and remove the support dir. Yeah. So I don't like this support dir. This support dir is kind of upsetting. So this stuff should probably go in there. This stuff should probably go in generic tinygrad helpers here. Helper's getting kind of big. Yeah, it's an L floater. Wow. It imports libc. We don't want elf in helpers if it imports libc. Okay. You guys are just kind of really watching me work here. Does tinygrad work with Mesa? No, we don't use. So Mesa, my understanding is that Mesa is a user space library for GPUs. So tinygrad just replaces that. We've done pretty well with line count. We're at 8461 right now. We can kind of go through what these things are. So the biggest file here is tensor. So tensor has all these methods. Look, it has docs now. Tinygrad's so unreadable. Yet you haven't read it in a long time. It's actually very readable now. And then all this docs just gets compiled to here, so you can see what's rand-n. Oh, here, normal distribution means 0, standard deviation 1. Wow, you can pass the device keyword. Oh, that's cool. Yeah, movement ops, then different ops, processing ops, unary ops. Everything's a method on tensor, which is cool. The docs became great. Thank you. Does your AMD driver support only RDNA 3? I believe so. It should not be hard to add RDNA 2 support. I think the only difference you're going to have to deal with is like the scratch stuff's a little bit different. How does tinygrad perform versus torch compile? Well, again, it all depends on your platform. So tinygrad natively, if you don't run it with anything, is slower. But if you run it with search parameters, and that's what I'm talking about here with MCTS. All right, so right now it's like searching for a kernel. So here I can show you something like so we like this example here. So this example is this is like inference on a ResNet. So inference on a ResNet, normally we're getting only 3 teraflops, 170 milliseconds, which isn't great. But if you run it with beam equals 3, now it takes a little bit to compile, which is, I'll run it with debug equals 2 so you can see the beam. So beam equals 3 is the old search. You see it searches all these different kernels. So before, kernel 0 was taking 2.71 milliseconds, and now it got down to 1.61 milliseconds thanks to beam search. We can also use MCTS here. So let's add MCTS and beam. So actually this one was already searched via MCTS. So you see that the hand-coded one, the one without any optimizations, took 2.7 milliseconds. The beam one took 1.6, and the MCTS one took 1.43. Yeah, so it searches. This is doing the MCTS search here. So you see that's the beam search there. This is the MCTS search. You see it already found one at 42. That's 0.16 milliseconds. The timings aren't that great on Mac. They're better on Nvidia. Yeah, so this one, when it actually reran, it was slower, so it used the built-in tensor core optimization. But yeah, so what are we searching? We're searching over all of the... Here, I'll run this with debug equals 3 so you guys can see what we're searching. So this stuff. These are all the different ways to represent the kernel. You see we're messing with the strides and the views, all this different kind of stuff. We're messing with some arguments to the tensor cores here, which axis it is. Oh, this is actually really cool. I've never run this before. Sometime we split the reduce axis, so you'll see 2 sums go in there. Now we're searching the next kind of kernel. So we search over all these different basic ways to run the kernel. Debug equals 3 totally makes it understandable. It's not that hard. Yeah, I'll break it down for you. So like, let's compare this kernel to this kernel. They're the same, but let's see what the difference is. So this one has a 16 here, and this one has a 4 here. So you see how this one, basically it, like, this explains it. So these blue ones here are the globals, the GPU globals, you know, like get global ID. These are the GPU locals, get local ID. These red ones are reduces done in a for loop. Purple ones are reduces that are unrolled for loops. And then yellow ones are upcasted. Okay, here. Do you want to? Are you interested in this? We can explain it further. So let's just do a little gem here. Well, first let me do it with no opt equals 1, so you guys can really see it. Okay. So this is a matrix multiply. That's 64 by 64 times 64 by 64. So we have 2 buffers being loaded here. You see why they have stride 0? This is my analogy that I always give. I talked about it on Lex. It's like if you have a cube, you can put matrices on the side of the cube, inner multiply, sum up, and that gives you the top matrix here. So, you know, put them on the side of a cube, multiply, sum up. That's the thing. Kernel, here's some meta parameters about the kernel. And then this is the actual generated metal code. So you see that these dark blue ones are global dimensions. Yeah. Now, it gets a lot fancier when we start enabling optimizations. So you can see this ran it in 41 microseconds. So with the optimizations, this is the hand-coded optimizations, it went down to 24 microseconds. So it's faster, and you can see this is the code that's generated. It's not that much more complex. Like, it's still very readable when you look at it. But basically, it expanded the, see that 244 at the end? It expanded the, well, I'll disable tensor cores for now. So we can disable tensor cores, which won't use tensor cores. It's not quite as fast. You see we're getting 28 microseconds. And then this is a 444, which is the absolute, like, classic. This is called coarsening in some GPU books. But basically think about it like this. It's doing a 4x4 chunk of the matrix all at once. So this is that 4x4 chunk of the matrix. It's accumulating into that 4x4 chunk of the matrix, and then it's storing that 4x4 chunk of the matrix. So each run of the kernel is doing 4x4 instead of doing 1x1. So that's kind of what that is. So let's take a look at a few. There's a few cool options for tinygrad 2. We can graph the UOPs, which shows you kind of what the inner generation looks like. The other big thing that I've been doing while I haven't been streaming is I refactored the linearizer into the lowerer. And I know these terms don't mean anything to you, but, well, if you follow tinygrad, they do. So this is what that looks like. And you can see that there are 16 loads. Well, actually, no, there's 8 loads. Yeah, there's 8 loads, 4 stores, and these are float 4 stores. You can see that's float 4. See, these loads are float 4. This is like the graph of the compute of that gem. So I'll show you guys one more thing. If I put debug expand equal 1, it won't actually render, but it'll show me a much simplified version of the graph before these expands. So you see there's these nodes in this graph called expand. And what that node basically is it just like, it pushes through the graph, expanding this node 4 times. So like this multiply is 64 times what's being expanded here is 0, 1, 2, 3. So when this node goes here, it actually runs 64 times 0, 64 times 1, 64 times 2, and that can be folded. If you're interested in seeing where that is, there's this file called UOP graph. This is in the expand pattern matcher here, and there's a function called doExpand, which actually runs that expansion. But this is what the linearizer became. And it's all written as these graph rewrite rules. This is the big chunk of graph rewrite rules, right? Some of the graph rewrite rules are stupid, like x times 1 equals x, x plus 0 equals x, x divided by 1 equals x, right? Like these are some simple rewrite rules. And then the rewrite rules get sort of fancy to do all sorts of things. Yeah, so when I run it with debug expand, it keeps all the expands and contracts around, but those can't actually be rendered, so it pushes them through the graph, generates a graph, and turns it into actual code. So this is what that code looks like without tensor cores. And you can see here it just stays as sum and mul. But if I allow it to use tensor cores are a feature of the GPU. So we'll run it with tensor cores here. There's this magic function called whammy888 float. It's fancy how it works. You'll just have to look up tensor cores if you're not familiar with, how GPUs work. You gotta just read. Yeah. So this is all those whammies. Let's put that with debug expand too, and I can show you like what it looks like a lot simpler, right? So it's basically one whammy that's just expanded across a couple of axes, contracts. Someone's gonna look at this and be like, "Holy shit!" Like, someone who's like been like messing with Triton, is gonna look at this and be like, "Holy shit, this is a lot nicer than what we have." I'm like, "Yeah, I know." And Triton's a lot faster. Again, they're very much more in line with like the PyTorchian way of doing things. Like, take the one kernel we want and make it fast. Don't focus on this generic abstract case. It's all about trade-offs, right? And as this is again, everyone in self-driving cars except for Tesla and sort of Waymo is like, Waymo's a fine project if you have unlimited money. But like, again, you meet all these people and they're just idiots, right? There's not like a redeeming factor. They're not making a trade-off. They're just idiots. But people in the ML accelerator space, people in the ML framework space are not idiots. They're just making usually different trade-offs than we are. Is TinyJIT search faster than JAX-JIT? Okay, so faster is a very, like, what do you mean by faster, right? On what platform, on what model? Saying faster in general doesn't really mean anything. Like, there's places right now where tinygrad is going to be well, JAX can do a lot of fancy fusions too. So again, yeah, it all depends on the... Why accept Tesla? Tesla doesn't seem idiotic to me. Tesla seems like, again, they're making different trade-offs from us, but we're all like operating in a world of modern engineering practices, whereas these older companies are just not, right? Like, you can watch a video with the Ford CEO. He's like, well, so we outsourced all the modules, and now we have 100 modules in the car, and they all have software in them, and then we realized that the problem with the car is the software, but we can't get the software because we bought the modules and they came with the software. So then we have to email this company and they never get back to us. Yeah, I mean, yeah, no shit, right? They took basically an old style of, this is still busy searching. They took like an old style of, yeah, if you're buying, metal pieces, going with suppliers is fine. If you're buying software, you shouldn't really do this, right? Like, you should have like an integrated, you want like a mono repo basically for your car. And, you don't want to deal with, well, there's a tiny piece of software running from this company and a tiny piece of software running from this company. So, yeah. That sounds sketchy for Ford. I mean, it's, yeah, like, I don't know. People say weird stuff like comma's sketchy or whatever, but like, I don't know. They don't really know anything, right? They're just falling back on proxies. And they're falling back on, well, but like Ford, I've seen their logo, right? Like, it looks like that, right? Like that, yeah, there we go. Come on, look, they have a logo like that, right? Like, clearly that's all right. We're not ripping off Ford, but like, when you compare this to comma, which has this like self-drive car folder, and this is just all the cars. Guess what? They're tested in CI. You think Ford has CI, right? AMD doesn't even have CI. Well, that's our docs. Why are those ones little and those ones big? Let's see. You think about how many lines of like convoluted C that is across Ford's platform. Yeah, Otto is just learning about Git and AWS. Yeah, see, that's what I mean. Like, they're clowns, right? They're not using real engineering practices, right? Whereas, like, again, when you compare us to our competitors, we're tinygrad, they're PyTorch. They know how to use Git, right? They know how to use Git. They got more stars than us. So, again, we're competing against real people. But it's so nice to be, playing. A lot of things about TinyCorp make me a lot happier than Comma. Like, there's things that are cool about Comma. Like, Comma's, if you like to like mess with hardware, if you want to like really understand how all the hardware works, I mean, we have such like a culture here of like we bought some of those Unitary dogs, we tear them right open, right? We just like know how everything works. We're building like cell phones from scratch in the basement, not total scratch, but like pretty close now. We're making our own SOMs. We have our own sort of pick and place machine, reflow oven, and we're like these aren't like, oh, we have these things, but then no, actually we outsource everything. I'm like, I'm not outsourcing shit, right? Like, the purpose is the process, right? The purpose is the process. What? Yeah, tinygrad goes as low as bypassing the GPU driver. Simplicity is the way to win. It is. It really is. I mean, these GPU drivers, again, they're a lot of the complexity in a GPU driver comes from supporting graphics. The compute models on GPUs are a lot simpler than the graphics models on GPUs. And if you can't write your own driver, so our goal eventually is to make chips. Again, we have there's a lot more work to do before we can get there. If you can't build a highly competitive framework on Nvidia, you're not going to succeed with your own chip. Will MCTS always be bottlenecked by the forward pass? Okay, so now what's slow in MCTS right now is the compilation time. MCTS is also single process, whereas Beam is multi-process. So, yeah, we can look into improving that. I don't know. This might just be a tutorial for tinygrad stream. If no Nvidia, no own chip. Okay, so Nvidia's chip is better than yours. Certainly better than the first chip you tape out, right? Your chip may eventually become better than Nvidia when you're on the 3rd or 5th generation of it, but the first chip you tape out will always be worse than an H100, right? Even regardless of like what you're trying to make, it's always just going to be worse. So if you can't build a competitive stack on better hardware, you certainly can't build a competitive stack on worse hardware. But Nvidia is not documented. Yeah, this doesn't matter, right? Like, the documentation you're going to have for your own chip, sure, you could read the Verilog, right? But like, how much Verilog can you read, right? There's some quirk in the PCIe, blah, 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 blah. It's just not tested. Yeah, so you're going to basically have to, if you can't build a competitive stack on NVIDIA, if you can't build something that's driver level on NVIDIA, why build your own? But yeah, so this is basically an NVIDIA driver. Like, you can read it. Yo, we're like succeeding at this. I haven't been streaming in a while. I don't know. It's kind of, maybe I stream because I'm miserable. I'm just not that miserable anymore. Things are actually working. NVIDIA is moving to more open source drivers. Again, like, you have to be so careful with what you read in the news. NVIDIA's had an open source driver for a long time, right? It's like GPU open kernel modules. They're just deprecating the closed source driver. But okay, is this really open source? I mean, there's this huge binary called the GSP. Here, let's go find it. I don't even know where. Where is it? Where is it? Lib? There it is. So here, let's go into this driver. So we have 2 GSPs, one for the GA series and one for the Turing series. I think that the AD series runs the GA one as well. Yeah, so like, if you like, if you call a 36 megabyte opaque GSP binary open source, then it's open source, right? Do they not even have strings in this thing? Junk strings. Huh. Some kernels require a pointer to HSA. Nimmelgen replied to me on Discord when... Wow. You're welcome to join our Discord too. I'm just typing there now. What do you do in a kernel to set that? Have that property be set. So, okay, apparently his answer was that you have to, here's where allocate space for the dispatch packet in the kernel args. So there's apparently some property of the code that's generated by the compiler sometime where it does this extra dispatch. So also when you go to this level, you see all the complexity that they've hidden, and a lot of times this kind of complexity is why your stuff's not fast. So once we start looking at this, so there's an attribute. Let's go find it in renderer C-style. In hip renderer, you'll see it. So you see this kernel modifier? This kernel modifier, see, there we go. It makes HLB CFAR twice as fast by basically specifying the max parameters it's going to launch with, because this has to do with register, there's a word for it. Basically, the register pool on GPUs is shared, and if you, God, what's the word? It's like resource exhaustion of registers. Register pressure is the word I'm looking for. How did we discover it? It's not insider knowledge. It's open source. You just read the code, read the driver. Here's the docs for the driver, right? CWSR enable. Default is 1 to enable this feature. Setting 0, disable it. Preempt shader execution in the middle of a compute wave, right? Like, of course that's broken. Yeah, reading docs. How else do you want to do it? I don't know. I don't really want to code on stream. I got kind of sick of coding on stream because, like, it actually teaches me bad practices, and it teaches you bad practices too. You like the stuff that's flashy, when in reality, I code a lot slower, especially now. Especially with the stuff in tinygrad where you're not really writing that many lines. And you just code nice and slow and, make sure it's correct. Don't spam code. Have we sent any boxes to the EU? No, we've only shipped US ones. It's such a pain in the ass to ship. The box weighs 90 pounds. Yeah, we got 2 of them over there if you want to say. Some tiny boxes chilling over there. Why do I care? You know that I stream for me, not for you, right? Like, we've had this discussion before. What chair? Is this the new keyboard? That's what you guys want to talk about? We wrote a line of code. It was a comment. I'll be right back. we'll do a little coding. So it's a little annoying on Metal because you can't actually parallelize this compiler super well. I kind of wanted to also say nodes per second. That'd kind of be cool. We want to know the number of nodes per second. We divide can I not do a nodes per second. We need to say nodes. I think we can just do that. I don't think we need that point. Actually, let's just get rid of the float entirely. Ugh. 3D. All right, so we get about 27 per second right now. We don't need that. Don't need that. See how that looks. All right. Do we like that first? Or should we put it over there? I don't really like that first. Well, I'm just tweaking something stupid. Okay. When do you think you'll start taping out your own chips? What do you think I'm going to say to that? See, look, this one searches a lot faster. Does MCTS always converge to the same optimal solution? Bro, I don't know what tiny search spaces you're searching. No. No, the search space is huge. So, I'll explain the search a little. So, this is the, no, not that. Where is it? So we have this thing called opt-ops, and those are the actions. Oh, it's in kernel. Okay, so these are the actions you can take. And then if you want to see, actually, that's not even real. These are the actions you could take. So we have something like probably 40 actions. Not all of them are available at every move. And then a kernel usually has like 7 moves, right? So it's 40 to the 7. So that's the size of the space you're searching. And like you get about 500 kernel runs, right? So you have 500 tests to search a space that's that large. Maybe it's more like 20 actions per thing. So it's, you know, okay, it's that big. So no, it's not optimal. But that's okay, because you can make some assumptions, right? If you were searching the space randomly, then yeah, okay, that'd be it. You can't search that space, forget it. But you can make assumptions that, well, here, you know what? I'll show you something. We have a convenient graph function called MCTS graph. So yeah, you can see it's finding the best one here. It's like 1.5, you know, 1500. The best I've ever seen it get is like 1450. But this one's probably going to stop at this 1521. 1521 is pretty good. Oh, no, it got better. 1504. Okay. So we wrote a graph out here. Let's take a look at that graph. So this shows all the nodes that were searched. So yeah, this should be about 500 nodes in this graph. It's actually a bit less than 500. Okay, so this is the root node here. So the root node we don't actually run. It's just for speed. There's no reason to actually run the root node. You're always going to do better with at least one optimization. So then it tries all the optimizations. You see it gets this TC1, which gets it down to 3,300. Does it actually spend all of its time on the TC1? No, there's other ones down here. It also does this TC1. See, like these are all like 3 pretty good actions. So the winning action turned out to be this one, which was 5. Then it went in there, did this upcast, got it down to 2,800, and then with that unroll, it got it down to 1,504. So these are all the search space, and you can see that like it doesn't waste time expanding a node like this, right? This one is 177,000. It's so massive that like it's unlikely that it's worth expanding that one. So we do intelligent search, where you know nodes that are pretty good are likely to be good places to look for more nodes that are really good. Yeah, this is like how tree search works. Okay, so we're getting 29 per second. Let's see if we can increase that. Our real goal is to get like like 500 per second. 500 per second would be a good speed. So then we can do this entire search in. So something I was playing with in the let's get stash pop. Oh, can we not get stash pop? We can't get stash pop. How do I look at the get stash? Get stash list. Whoa, look at all these stashes. Git stash show. Yeah, okay, here. So we added this early check to not waste time compiling early check for same AST, optimized AST. So right now, what we do is so sometimes you get to two nodes and they're actually the same code. So like different optimizations ended up leading to the same thing. You should all be caught by the AST check. Need to fix. Canonicalize. I talked about this in Discord. Quazzle is making progress. Challenges with loop unrolling. Cool. That's what I will look at later. But so this is it's an early check for the same AST, so we don't actually have to put it through the compiler. We'll import lazy op here. So this check should always be correct, if not always complete. Basically, so it goes to the current node, it gets the optimized AST, and then it sees if it's already seen that AST before. And if it's already seen that AST, we just remove the node and we continue. Which is also kind of wrong. I think what we actually want to do is this. Yeah, that should be right. All right, let's see if the searching is faster. $30, okay. We only expect to get a little speed. We don't expect to get a ton of speed from that. That seems a little bit better than it was before. It's actually pretty much the same. That's the same as it was before. Oh, look, but look at the one we hit. I mean, it's just luck, but you see that we got a better outcome here at 257. So we can look at that graph. And again, it's the same graph of the search. We just got a little bit luckier about how we expanded the nodes. So yeah, I mean, it's within a couple percent. You see that the difference between it's 2x better than the hand-coded one, and the hand-coded ones on Mac are pretty good. The hand-coded ones on Nvidia are terrible. And it's just because we really put effort into it. Cool. So one of the things we can do is we can just mock out this rollout function. And then we can see how fast everything is. So if we do a mock rollout, wow, look at that. Look at that speed. Wow, 2,000 a second. Wow, rollout's slow as shit. All right. So this is the thing that we can parallelize with a lot of work, actually. With a lot of work. Oh. So I changed this function to be a sample function. This is Chen-Yu's idea last night. This uses, it's like basically does a softmax and then a random choice. It samples from the tree instead of like taking the max of the UCB. It's like Monte Carlo tree search. You can read this, by the way. It's an extra MCTS search on tinygrad. It's extra because it's not ready for the main code yet. Yeah, so we found out where all the slowness is. And all the slowness is in, well, actually we haven't found out where all the slowness is. Is the slowness here or is the slowness here? Let's just check quickly. So useless. This is the code that Copilot would probably help me write. Actually, probably not, because I'd probably waste a ton of time reading the code that it wrote, and just like it's faster to just do it. All right. Well, that's interesting. So it looks like it's spending about half the time on compilation and half the time on running. So we can also turn that down to 3. Didn't really help much. And even within compile, that can be further broken down. Interesting. Okay, so most of the time is spent in the compile function, but a sizable amount of time is spent in the runtime. This isn't allocating buffers, is it? No. Buffers are pre-allocated. I didn't do anything stupid in here, did I? Clear L2 is false. Make sure that isn't actually hitting. No, it's just slow. Wait, okay, so why is it so slow? Versus TM, right? So I'm looking at the actual time spent in like the Python loop versus the time that it's telling me it actually took on the GPU. Oh, and then there's another hack here too, which is like there's a hack for globals, which doesn't actually run the whole thing. None of these are actually running the whole thing. Well, that's slow as shit. Okay, well, that's actually spending all the time on the GPU. So we have a hack to work around. Interesting. I didn't realize how much that mattered. Look at, like, all becomes GPU time then. Actually, I want this as a percent. Is that right? Okay. Wow, and that's actually all the time. None of the time is spent anywhere else, which is interesting. Okay. So to put this guy back, that goes there, that goes there. Starts to become overwhelmed by the compile time. So there's not really much we can do about the runtime, really. Three should reduce the runtime percent a bit, but I guess it doesn't really matter. Those kernels are all fast. Any slow kernels get hit by early stopping. So we have this thing called early stop. Actually, am I bugging that? Okay, so we're multiplying there by factor. No, so that's actually right. Cool. Like that extra letter. How do I easily, like, I make that colored, but I don't really. Can we nest F strings? We were just talking about that you can. Colored. Well, compile time should be Scion, and flatten's not used? Why is it imported? Runtime time is red. Let's see how that looks. 25 is not in list. Oh, did I do it backwards? Yeah. Yeah, I've been listening to the new Say Anything came out with a new album. Max Bemis is proof that you don't have to, you know, be boring when you're old. Um, fan fiction, like it's really the a lot of these like emo bands, they just like completely mellow out. Think like Good Charlotte writing Centuries, right? And it's just terrible. It's just this absolute generic, pop music that no longer sounds like Lifestyles of the Rich and Famous, right? But Max Bemis has not sold out. My life might end up shorter than yours, but it's quality, not quantity, you thimble-dicked man whore. It's just like, your therapist knows you're a failure. Eminem came out with the whole album. I liked one of the songs was pretty good. I mean, it's still the same, like, and Detroit was hard, where I grew up in Detroit and it was hard and I came up from nothing. Yeah, I'm Eminem. Yeah, right. Like he's still on about that. It's like, it's kind of like when people get older, they get like froze in their ways. Like he's still very talented, but it's not new. Whereas like, in some ways, I think this is like evolved. Like what he talks about, and it's relevant. I sympathize with it. Like the song's called fan fiction. Like it's about the parasocial relationship between like the fans of a band. And I don't know if like I'm the only person who like listens to these, like like if Panic at the Disco comes out with a new song, right? Like you're not, like you have to deal with basically this problem. Yeah, just mind blowing. I probably listened to the song 100 times. Oh, it should be possible to determine runtime of a kernel without doing all these computations. Good luck. Good luck. I have tried. And I mean, the cool thing is you can figure out exactly, how accurate your estimator is. So yeah, try to build an estimator of. No, I like them better in the thing. Try to build an estimator of kernel time without actually running the kernel. I think you'll be shocked at how hard it is. Okay, so this part can be entirely parallelized. But this part can't. So what does that get us? Like 3, 4x? It's actually probably worth it. Make a branch. There's a very detailed cost analysis in LLVM. Yeah, exactly. I'm not writing that shit, right? So there's like, the thing that you want probably isn't the thing you want, right? The question is not, given this kernel, given these kernel arguments, how long does it take to run? You're never going to build a good estimator for this. There's so many things that interplay. But where the low-hanging fruit is right now, if you do want to improve this search. Now, again, I caution you about trying to improve this search, right? So if you want to improve search such that it runs faster and gives you the same answer, that is a straight up win. But if you're trying to improve search by being more clever, How exactly have you figured this out, right? How exactly, like we don't have a framework for evaluating whether the new search is better than the old search. And all the work's in the framework, right? It's the same thing at comma too. Like so much of these modern machine learning-ish things are just about figuring out the correct test framework to see if you're making progress or not, right? So you make some tweak to the search and you run it on one kernel and it does better. What does that mean, right? Does that mean the search is better? Who knows? So Stockfish solves this problem in a very elegant way by having a tweak of Stockfish play against a whole set of older versions of Stockfish. And you can just take a win percentage, and that's pretty good because that's the exact thing you're trying to optimize for. So what you're trying to do here is you're saying, well, okay, so I made something. It's faster on my computer or on my kernels. That doesn't really say anything, right? This is what I mean. Like, if you get speed, it's a straight up win. But if you get a smarter search, well, is it smarter always? Right? There's no free lunch in search and optimization. There's no free lunch in search and optimization. So, but if you are interested, the answer is probably not figuring out how to estimate this, but the answer is figuring out, well, I guess it's sort of estimating this, but the answer is figuring out which nodes are worth expanding and which nodes aren't expanding. So you'll see if we have unexplored children, we just use random choice here. We also use random choice right here if we just expanded a node. So random.choice, whenever you see a random.choice, you're always like, well, but some choices are better than others. And yes, some choices are better than others. So that would involve putting a prior on the actions, right? So you're at a node, you want basically a prior over the action space. Now, there's a few ways to get that prior. You could get that prior online. I think that's something, again, you're going to spend 95% of time on your evaluation harness and 5% of time actually implementing this sort of code. Well, yeah, there's hyperparameters too. Here's two hyperparameters. We have a temperature of this sampling, and we also have the C from the UCB function, which is math squared of 2 for now. So yeah, tweaking those hyperparameters may get you better results, but the question is, does it always get you better results or only sometimes? So yeah, by putting priors on those random choices, you could probably do a lot better. Chen, you and I discussed a simple way to do the priors yesterday would just be to figure out which kernels improve runtime, right? Just overall, which kernels have I selected, which optimizations have I selected given this kernel that have improved runtime, and search those first when you expand new nodes. This is probably a good idea. I bet this would improve search efficiency like 2x. Then the other thing you can do is you can build offline models, right? So offline, given a device, you can figure out that that device is more amenable to certain kinds of optimizations than others. And yeah, you can have that offline prior. And then the cool thing about priors is you can multiply them together. And generally, if you have two good priors that come from different, multiply them and let's just be better. So yeah, there's that. But again, the main thing you're going to have to build before you start playing in that direction at all is a robust evaluation harness that evaluates the effectiveness of your search across a wide variety of hardware and a wide variety of kernels. Whereas if you just want to work on speed, well, speed's just speed. If anyone, all right, can we ban the B word and the T word, any of that stuff? It's all banned. It's all banned. The B word and the T word, that's it. That's it. What kind of camera is this? It's the same one I have at home, I think. God, now we bring them up. You see, you can't even say them, man. That's right. I was referring to trains and buses. We are not discussing trains and buses. T word and the B word. Long live trains. So if you want to follow along, it's in the parallel MCTS branch on tinygrad. So, let's see what crap I wrote to make things parallel for Beam. Part of the problem with parallelizing on Mac is that you need the device open in order to do compilation. We also kind of want to break compilation down into 2 steps. There's a lot of complex crap here. Let's just get rid of this. We don't actually need this. Dev compiler. So there's 2 different steps here. There's the to program step and the compile step. And we could, don't do that. No, not that one. Where was it here? Okay. So we could actually break these out further. Let's just stick this one here. And then see how much time we're still spending on compilation. Yeah, not much anymore. Okay, so it's really all just that, which is cool because that can be parallelized. To program can be parallelized. Wait, what? No, okay. Let's get a pool going here. So there's to program and there's compile, and they're separate things. And sometimes compile can fail. To program should never fail. If to program fails, it's a bug in tinygrad. Wow, that actually worked out to be less lines than using the stupid try compiled linearized with IDX. Oh. So this lowering is all in Python. I wrote this crap. So you see, okay. You see how much we can speed up by, why is it faster now? It's just faster now. What did I change? Oh, the signal crap. How much time are we spending on that? You see, no one benchmarks any shit, so it's just slow. And the combination of Linearize and UOPs, I don't know how much of that is not reused anymore. Oh, I run that twice. Wow, I run that always? Oh, that's kind of annoying. All right, well, that was a big waste of speed. There's a big speed regression there. We can fix that for Beam as well. I mean, we need this to be in a shared framework. Wow, there were so many regressions when we went to the lower. Everything's so much simpler now, though. Cool, look at that. Look at how much faster we're searching. Love it. That was completely free. We made things both simpler and faster. No parallel Where are you going? What was it before? Was anything like 24? Yeah, 33% faster. Guys, we're winning on this stream. Free lunch in search. That's right. We found a free lunch in search. We just stopped running the function twice. That's cool. That bug actually exists. And I mean, my whole next week is going to be spent on search. I don't know why I posted it in the employees only channel. We have a breakdown. So we have 5 people who work at Tiny Corp now. One's on vacation next week, so we have 4 people. We're all going to take a different part of the speed problem. We're going to work on our own part of the speed problem, and this thing is going to be faster than Torch in no time. Wow, I love my new fast MCTS. Okay, so there still is a 2x to be had. You can see these percentages don't add to 100, and it's because I put the lowering outside the time. Does that make sense? It's turned into a pretty good stream. We're actually coding. Look at that. I mean, we had so much good gains in time programmed. Do we want to try to parallelize this? Parallelizing is annoying. Still have to do multiple sample trees. This crap all looks slow. Look how slow this all looks. No, what here is actually slow. Can I decorate this with profile from helpers? That'd be cool if I could. Does this function as a decorator? It does. Context decorator call takes 2 positional arguments, but 4 were given. I think I have to like tell it stuff. Maybe that. Come on, profile for me. Yeah, profile shit. Alright, so where are we spending all the time? Ton of time spent in C-style render. Wow. Wait, why is that not sorted? Oh, it's sorted by that. Oh, C-style, I know, C-style render just because that's where it's doing the UOP graph. Okay, so half the time is being spent doing stupid UOP graph. We know how slow a UOP graph is. Oh, here we go. So here's ops metal compile. Ops metal compile is actually a pretty small part of the time. Wow. Spending a lot of time in symbolic floor div. This symbolic and UOP shit is so slow. Okay, but that's cool. So almost all the time is being spent in two programs. Well, not almost all, but that's a percent. Wow, look how nice tinygrad's infrastructure is. That profiling just worked like that. That was cool. You understand the stream so far? Great. We're trying to be more understandable and approachable for everybody. Except noobs. Okay, well, that's pretty good speed up already. If we want to parallelize this, I don't really want to parallelize this. I just want to make it faster. I hate how slow this is. So part of the problem with parallelizing is then we'd have to do like, it would actually be slightly different if we were to parallelize because we'd have to sample from the tree more. Like you'd take multiple samples from the tree and then run them and then like backprop them all when they come in. Hmm. $35 a second, $47 a second. Tinygrad's infrastructure is so good. This is so nice. Like, it's so easy to write things like this. That is how you make progress. I was thinking about that. I even thought about tweeting it. It's like, there's really one group of people that moves the world forward, and that's the people building infrastructure. Think about the tech tree of any game. We're progressing through that same sort of tech tree now. I know a lot of people are like talking about this stuff now, but it's cool to to be explicit about. Like, we're moving through a tech tree, and the way that you move through a tech tree is you build infrastructure. I don't know. That's kind of like what I do with my life. Eventually, I want to rewrite like all of OpenPilot in tinygrad. Like, tinygrad's a programming language, but it's a very restrictive programming language. It only lets you express certain kinds of operations, but these certain kinds of operations are pretty much all you're going to need to build like brains and stuff. So yeah, like a lot of OpenPilot can be rewritten in tinygrad, and then it's the job of the tinygrad backend to actually make that run fast on hardware. The first chip that we tape out is probably going to be it's probably going to be an inference chip for comma. Like once OpenPilot's ported to tinygrad, we can then switch comma devices to use tinygrad taped out chips. It's a lot cheaper to tape out a small chip. I mean, we would have to care more about power, but you have to care about power anyway. So it's good to like, you start with the mobile ASIC and then you blow it up. You know, as much as they piss me off, I think like Qualcomm's undervalued. Like, let's look at Qualcomm compared to AMD. 204 billion. Oh, similar. Unbelievable. Unbelievable, guys. It's really yeah, no, I think that like I'm actually bullish on, if Qualcomm understood like what they had and what they were doing, I'm actually bullish on them building better neural network accelerators than like AMD, for example. All right. We have faster search. It's a question of making this faster. Why? So it's a kernel, right? I give it a type. Does it still pass? Where's my MyPy incantation? I don't know why when I run this in CI, this is the MyPy that runs in CI. It doesn't include the MCTS, but when I run it there, okay. Incompatible. Oh. So if you're interested in making this faster, I think we should just probably focus on making lowering faster. I know the branch is called Parallel MCTS, but the longer you can, like, parallelization is always going to be a trick that's available to you. Whereas if you just can straight up make improvements, there are just wins out there. So this one, unfortunately, is something we tracked pretty well already. So I don't know how many gains there, like low-hanging fruit gains there are. There's definitely gains. They're just not that low-hanging. Almost lunchtime. So I have this thing called external benchmark schedule. Yeah, we're getting like 653 there. And 653 is an improvement kind of from what it was. But you can see that like this is 10x slower than all the other steps in the model. UOPS is the thing we were running twice, by the way. It's this model Linearize that's running all these graph rewrite rules. So this is the thing that's new in tinygrad. And the old one was slow too. Like it's not like the old one was fast. But yeah, we've moved to, instead of like hand coding rules that writes this code in a linear way, things have been rewritten as graph rewrite rules, right? So like this is the matching pattern, and then this is the code that runs if it matches. You can see the pattern matcher is here. So yeah, there's a lot of gains to be had by like instrumenting this, and like I have some things to speed it up. That's kind of what's my pattern matcher? Here's pattern matcher. So like I'll compile like a dictionary so I can do a fast dictionary lookup. But in theory, I think you can do this recursively. There's also probably a lot of stupidity here in like how we iterate over these things. So you can see that if something's a list, I just create a list of all the permutations, which like it's correct, but there's probably a smarter way to like do that. Like I think greedy is fine. It's greedy with a tree. It's just, I mean, it's nice because it's an easy thing to write, but I think a lot of time's wasted there. I mean, and this list comprehension's all pretty slow. So let's see. If I could make that 2x faster, then we're looking at something like 60 nodes per second. I want to get that to 500 nodes per second, but there's no way we're going to get it to 500 nodes per second, right? Like even if the only thing was GPU runtime, which I can't parallelize at all, right? This in theory can be parallelized. It's just a little annoying on metal. So this red stuff can never be parallelized, at least not the way tinygrad works now. You could, in theory, parallelize it across GPUs if you have a multi-GPU computer. But yeah, so 40%. So, wait, that's 25? I thought it was 30. It was 30 before. Why did it lose speed? Oh, maybe sometimes it's faster than others, depending on the nodes it happens to search. Hey, look, this one's faster. Interesting. Wait, and this one like messed up. Look, this one didn't find a good one. This one found a good one and was faster. Whatever. Yeah, see, and that's the other problem, right? Again, the search is all heuristic based, so sometimes it gets to a bad one. And then, you know, you do all these stupid things. Well, why don't we just put the search in a loop and run it 5 times? Well, yeah, you just got 5x slower. Can you parallelize that? Well, sort of, okay. So if we're at 30 per second and we're spending 38% of our time on runtime, yeah, the best we could possibly do, even if we got the others to 0, was 78. And that's not fast enough still. So it's, there's no getting around just, yeah, like this. All right, so like sometime the time is spent in a net, and sometime the time is spent in, to the code and realize. Construct this compiled runner. But it really wants a line profiler on this. Interesting. So most of the time isn't actually spent waiting for the kernel. Most of the time is spent constructing the kernel, except in like some weird cases where the kernel's probably already constructed. Net, that one's all in wait check. Why is sometime this fast and sometime this slow? We're doing it precompiled, right? Yeah, precompiled equals lib, so that gets bypassed. That's not running. Device, nothing slow there. So let's just all be the metal constructor that's slow. Not triggering that. Dispatch data, create new function with name lib. You know, we're actually already creating this program when we compile it. Or are we? Library. Yeah, see, like this is calling new library with source, this is calling new library with data. So we sacrifice a little bit there. We ever hitting the compile cache? No, well, wait, this is all after that. Yeah, so sometime the time is spent in wait check and sometime the time is spent in the net. Wish I could aggregate these somehow. Okay, and this is happening before this, so we wait check. Yeah, you see it's like a decent multiple of this, right? So we're spending, so it's telling me that the kernel runs in 4 milliseconds, and then it's spending this long running it. Which, yeah, again, there's not really going to be a way around. If you have a 4 millisecond kernel, that's just how long it takes. This only seems to be slow sometimes. I wonder, why is it slow sometimes and not slow other times? Well, let's profile it. Can you just do that? Great. Slow sometimes and not slow other times. We don't have any more information on that. Oh, maybe it's this GC. I don't know, maybe it's just running something still on the GPU and it takes a long time. Okay, nothing sketchy in wait check. Yeah, I don't know. I mean, this is just how long it takes. These are big kernels too. Like these kernels are on the order of milliseconds. So if you have kernels, if your average kernel is 3 milliseconds, you're running it 3 times. Okay, well, one thing we can do is we can lower the early, where's early? We have early stopping. This probably can be 3 and doesn't matter. All right, 40 per second. Yeah, cool. I don't know, like, I doubt that matters. The question is, it definitely made things faster. 3 might be a little aggressive there. So what this is, what do I set it to in Beam? I do 3 in Beam. Three is probably fine. Again, I need that framework to do proper evaluation of these things. Like, you could just get unlucky and get a slow one, and then it exits and it's done. I mean, 3 is what I do in Beam, so it can't, like, be that. I don't know, like, it hit there, but that could just all be lock. Seems like I get most of the games with 5 anyway. So what this is it'll only run the kernel once. If it's... Should we adjust Beam to match? Beam is so wasteful now because it's not even doing that compilation correctly. Okay, 36 per second. It's pretty good. You see MCTS is winning most. So like we have the hand-coded optimizer, the tensor core optimizer. I can put Beam in there as well, and we have MCTS there. Wow, that's still going. That's so slow. Let's switch to parallel MCTS. I didn't push yet. I now pushed. So the stuff is cached, so you can see that's all fast now. 34 per second. Oh, but look at this. 69% of the time is spent compiling, and only 1% of the time is spent on runtime because these kernels are so much smaller. Actually, that's probably also going to be true. I happen to be running this on something that has big kernels. But if I run it on something without big kernels, JIT beam means only beam the things in the JIT. So you see all that stuff's not in the JIT, so it doesn't run it. Now as soon as we get to something in the JIT, the trade-offs become different. Why is it doing this? Let's fix that bug. Probabilities contain nan. I exclude the ones that are infinity. See what's going on, why it does that. Oh, that's a different problem. Cool. Well, yeah, because we no longer put the compile in. No, this is a tinygrad device compiler error. That's fine. I mean, it's still interesting. But yeah, this should not be, this should be except compiler. And we'll change that to include compiler. But yeah, that's a bug. If someone wants to look into that. See, this kernel is very slow, so we're spending 90% of the time on runtime. Okay, same bug. By the way, does math is inf work for negative infinity too? We got through all that. Is that a good time? It seems pretty good. 7 milliseconds. Who knows if it's good? Look how much faster the search is on these. We're almost getting to that 500 per second. 239 per second. This is a slower kernel, so it's not that much slower. So I mean, though, there's so much diversity in these kernels. Like, you do something to make it faster for one. Now, there are real wins, but go to the bathroom. I'm going to grab a matcha latte, and then we'll do some questions, and then that's the end of today's stream. We got to look into that HSA thing. That's crap. That should just be removed. We should exclude those kernels. Search is really addictive to watch. You can just sit and watch searches. Wow, it's searching. Look at it search. Oh, yeah, someone want to look into this not folding crap? Like, I know where that code is, but you want to see if you can fold those? That would be a cool thing to look at. And you can look into some of those bugs and see why the linearizer doesn't always work. Oh, perfection. You know, we pursue perfection in tinygrad, and I hope someday we'll be there. It's true that we have, like, tinygrad used to have different looking bugs. The bugs now are like deep bugs. There aren't many shallow bugs anymore. Which, I mean, I guess that's how bugs work. Good progress made today, yeah. 8,461 lines. We get a matcha latte and we'll do questions. Wow. We got energy from caffeine, focus from theanine, clarity from lion's mane, and calm from ashwagandha. That sounds lovely. You know, they never sponsor me. Taika, you tag the sponsor, you know. Lion's Mane, Big W, all right. Probably because of my rants. No. Look, what's politically correct, just change it. Maybe stream more often. Nah, not worth it. I'll buy my drinks. So a good time overall for this is if it's sub 20 milliseconds, we're doing really well. So this will finish shortly while we do questions. Appreciate the more educative stream. I want to get more people involved in tinygrad, both usage and development. I think it's now to the point where it's quite usable. Unless you're doing these searches, the speed is still slower than Torch. With these searches, it's competitive. Like if you do like Beam 3 or MCTS 500, it's competitive with Torch on most platforms. It's definitely competitive on Mac. It's definitely competitive on AMD. On Nvidia, it's probably still a little slower. You couldn't get it to work on your 3080? It should work on 3080 now. Where we support all the... It works on my 3090 and it's the same chip. So yeah, it should work fine in the Envy backend if you have a 3080. Try it right now. Can you cache the search across runs? Yeah, it's cached automatically. So yeah, you only have to do the search once. I did hear about Carpathy starting Eureka. I like that for him. Seems chill. Are pie trees ever coming to tinygrad? I don't know what a pie tree is. So probably not. What? Why would I want this? Oh. I see. We kind of have some like implicit stuff that does this. I'll show you the function. You mean like here? Like we have functions like get parameters, which will like get state dict. This is kind of like a pie tree. What exactly do you want pie tree to do? Can you solve the arc challenge using tinygrad? Maybe you can. Isn't named tensor axis? We don't have that. Apparently PyTorch had it and deprecated it. Maybe just map scan over pie trees. Stop it. Stop it. It looks so ugly now. Can you reduce the kernels in size for faster running? Yeah, so we actually do that. So there is, in my time kernel function, you see this thing called factor? So this will reduce the global size and then return a factor and then run it and use that as estimation. So that's already being done. What else we got? Oh, on your 3060. I think that one's supported too. Sorry, that's not the same chip as the 3090. If it's not supported, it's probably a very small change to make it supported. We're interested in supporting everything back to like the Turing series, like the 2080 series. Jax also has higher order gradients. Do we not? Can I not just grad twice? All right, so we got 21 milliseconds. Could be better. By the way, it caches, so you can see it'll just run through the cache again. It's very fast the second time. We got 21. I've got 19 before. That's what I mean. Like the search isn't. Search ain't perfect. Wow, repeated stores and UOPs. Interesting. Yeah, what we need to do for all of these things is we need a context that this is great at finding all sorts of bugs in tinygrad. We need like a context that prints out what, like, see, we have tensor operations. We need another one of these that says, like, that prints out the kernel that's trying to be lowered, right? Like you see like error lowering meta ops kernel. We should print that kernel out. Oh, actually, I should just be able to... Yeah, why do I only print the op there? Will we hit that again? Nope, we don't hit it again. Tragic. So we can print the kernel there, but that still doesn't even print the... All right, we need to do the refactor. The lowering should have... Okay. The schedule should be optimized separate from running. Yeah, so the AST should be lowered. So in this MCTS search thing where we have the this get optimized AST, that should actually be like pre-run. And that's what the beam search is. Not, it doesn't return a kernel, it returns an AST. Yeah, I believe it's just grad twice. Hessian is a matrix. I don't know. Do I still have my old cache? Interesting, that's the old cache. I'm not getting 19s now. Sometimes I think it's dependent on like how hot my computer is. Or dependent on like something. We get like lucky with the RAM allocations and they're not like strided on pages or something. Who knows? Apple we have a lot less control on because we didn't write our own driver for Apple. Like the Apple backend here you can see just uses like normal metal stuff. Like here's metal program. We just do like, you know, new function with name, new compute pipeline with state. So yeah, it's not as low level as the wonderful. The AMD one's easier to read than the Nvidia one. The Nvidia one has a lot of crap that hasn't been cleaned up yet. But like I love this. Like that is how you launch a kernel on a GPU. And we're gonna get this removed because we don't need that. That's not real. Release mem is such a misleading name. These need better documentation. 3 and 0. These need to be better documented. This update API is interesting. So this is how we like update things in the JIT. We update the queue. I don't know of an obvious better way to do it, but I wonder why it's slow. Oh yeah, here we can. Let me show off something else to you guys. So we can run llama. This is llama sharded across 4 GPUs. So those are the weights. That could be faster. There's a reason why, yeah, that's not getting us the full speed, but yeah. So we're getting 138 tokens per second across 4 GPUs. I believe now across 6 GPUs it's still slower. So this is Llama 7B unquantized on a tinybox. So once you go across 6 GPUs, it actually gets slower because you see, even with our crazy good drivers, We're still spending a lot of time here on NQ. So there was a PR put up this morning to lower that. But you see, again, if you're using CUDA, you have no control over your NQ time, whereas I don't exactly get how this works, but keep state around. But look at that, it halves the NQ time. Yeah, so across 6 GPUs, we only get 89 tokens per second. This is still a little bit under what GPT Fast can get, so we have some work to do still. All right, do we have any other good questions? How do you build superintelligence? Right now, have kids. Start by having a high IQ and then have kids. And then, train your kids to work together. That's the most straightforward path to superintelligence. Teach your kids tinygrad. What do you need to know to understand this? What domain of programming? I don't know. I didn't like learn it in school or anything. I've been working on tinygrad for it's been like 5 years. It's been a long time. But like we're getting close. Look, we have docs. Like, if this wasn't legit, would there be docs? Like real docs. How is inference speed compared to Llama CPP? So a lot of those things are focused on quantization. Again, if what you're trying to do is just run Llama, like use Llama CPP. It probably is going to be faster. The idea is, like, the whole theory behind tinygrad is the bitter lesson. This is one of the things I always shell for. The biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective and by a large margin. The reason for this is Moore's law. So, where is he? Here. One thing that should be learned from the bitter lesson is that the great power of general purpose methods are methods that continue to scale with increased computation, even as the available computation becomes very great. These two methods that seem to scale this way arbitrarily are search and learning. I wouldn't use the word learning, I would use the word optimization. But yeah, like search and optimization scale with the compute. By the way, this is a great thing to read. If you haven't read it, I shell for it on stream a lot. But that's kind of the difference between tinygrad and Torch, right? We don't specify what we don't write the kernels. We specify a generic framework with which we can search for kernels. And as search methods continue to improve, tinygrad is kind of this new class of compiler that's like, so there can be search at every level too. So all of this search is being done at this level called kernel.py. So these are those optimizations that we talked about, that search space. But there's tons of other potential searches. So for example, I'll give you one here. Here's a function called image.imageconv2d. So this uses textures to represent the inputs and outputs to a convolution. If you're using textures on a GPU instead of buffers, mobile GPUs in particular, they put a lot more effort into their texture cache than they do into their buffer cache. So on Qualcomm, this is like 3x faster, like on the Com 3X. So this is mostly written for Com, but like this stuff can be searched, right? How we choose to represent them right here is hand-coded, but that can be searched. So you can search at this very high level, right? And we have another file called schedule.py, and this is the scheduler that determines what order kernels are running. This stuff can also be searched. It's effectively a topological sort. So we have two big topological sorts in tinygrad. We have the topological sorts that determine what order kernels are running. Then within there, we have a bunch of graph transformations. And then we have a second topological sort when we actually turn the UOPs into a list. Those UOPs, which I showed you in those UOP graphs, remember the UOP graphs? So like this is a UOP graph. When we turn these UOP graphs into a list and fundamentally a program, we have to determine what order we put them in, right? And that order is not fixed. There's multiple. So the only rule is that the order has to be a topological sort on the graph. If you don't know what that is, look it up in a computer science textbook. But within topological sorts, there's many lists that satisfy the property of the topological sort. So yeah, you can search there as well. And eventually we're going to abstract all of this out into a very powerful general search framework and be able to find the absolute fastest kernels to run all of this stuff. And like when you're talking about something like, when you're talking about a training run at like GPT-4 scale, or even bigger, when you're spending $100 million on a training run, if you can somehow make it 1% more efficient, you save $1 million. So you're willing to put tons and tons of compute into this search. It's a question of how well the search scales. Can the search continue, right? Can you keep searching for better kernels? And the answer is sure, right? Let's just do one as an example, right? I don't know. What should we set it to? 5,000? Like it'll just work. Yeah, it's annoying. It's wrapping. Let it go. We'll see what it finds. I don't know. Does it get better? I've never ran one for 5,000 before. But like the beauty is, as we make this faster, right? We could parallelize it. We could make the Python faster. This method only becomes more effective as computers get faster, right? When Apple releases the M6 chip, it's not going to require any like hand work, right? You can just increase your search budget. You don't need to think about what the GPU is, as long as you've captured all of the, everything you need fully flexibly, then let it search. No, don't do that. Stop wrapping. Make it a little bit shorter so it doesn't wrap. Would you like to know how the AMD accelerators are? Yeah, we disabled the broken feature in their driver. And we wrote our own runtime, and now it's fine. Oh, look, we found a faster one at 2028. Look at that new record. That's a new record for that kernel. I've never seen a kernel be that fast before. And it searched 2028 kernels to find it. That's on analog computers. I don't think there's big gains to be had. You give up a lot when digital computers run 100% repeatably. You don't really need this property, but it's annoying to not have it. It makes debugging stuff really hard. So no, I don't think. I think that what we're going to start to see is smaller and smaller data types. Nvidia talks about this a lot. Like if you can make training work on like float 4, that is really power efficient because most things scale with the square of the multiply scale with the square of the operation size, basically. You can think about it just as a generic table, right? A generic like 2-op table where I have x here and y here, right? It's a square. So am I searching randomly? No, we're using Monte Carlo tree search. It's a guided search, right? So no, we're searching over a set of permutations, right? Like I showed you how that works. Yeah, CrowdStrike needs it right now. Green tinybox is greater than red. To be honest, the red one's probably a better deal. It's $10,000 cheaper, right? Like, how much do you want to deal with annoying drivers? The answer is Like I said, one box gets bought 10x more than the other, and I'll leave it up to you guys to decide which one. Multiplying huge integers using Fourier transforms. Oh, it's even faster. Yo, we've never seen a kernel that fast before. Like, that's a new record. We just needed to search 4,854 kernels. But imagine we got that 23 per second up to 2,300 per second. Can I summarize why they're worse? Because AMD is bad at software. It's really just that. Like, Nvidia invests into software and AMD thinks you don't have to. And like, they're going to lose as a company because of it. Oh, look at this. MCTS just continues to get better. I don't know what HVM is. I don't know what symbolic ML is. I don't think this stuff is... Oh, look. Look at how long it took on that one. It hung. This kernel's a lot simpler. So, like, it gets into the weeds, right? Like, if you tell it to keep searching, it will keep searching, but eventually it gets into the weeds and starts finding, like, dumb kernels. I think I got my stop condition correct on MCTS. So, like, I have, like, MCTS when it exhausts the tree. You kind of have to, like, deal with that. It's a little annoying. See, you can just put more zeros on this number and it does better. What if we searched for 50,000? What would we find? Thank you. Yeah, I like the colors too. It's cool. Like, you learn to read these really fast too. Like, these are really simple. Globals, locals, reduce, unroll, upcast. Right, and then they're in the kernel name too, which is neat. How many kernel permutations? We went over this before. It's 100 million. Well, yeah, maybe if you like prune them down, maybe it's like 10 million. But yeah, I mean, you get even 5,000, which is crazy high. Like, you get 500 test points in a space of, like, let's say 10 million. Do you know if the search space includes very fast solutions? Well, I mean, what you can generally do is you can plot, and the thing looks like it converges kind of to an asymptote. So I would doubt that there are, like, magical super fast solutions. So, okay, actually, I can tell you something we definitely know. So the GPU in this computer is an Apple M3 Max. So if we go here, this is not here. Wow, Apple has a lot of different. So the M3 Max has 14.13 teraflops of compute. So we are at 86% pretty much, 85.8% efficiency on this kernel, right? So it can't be faster. The fastest time that you could possibly get on this kernel is going to be, 1.43 divided by that. Sorry, multiplied by that. Yeah, so the fastest time you could possibly get is 1.22. %86 is good, yeah. Multiplication on log numbers is an add. That's true, but what's an add on log numbers? That's what's annoying about that. Yeah. 86% MFU. We're trying to get our training MFU up. Our training MFU is not that good yet. Our training MFU, well, it's not bad. Our training MFU for, like, ResNets is like 33% on the tinybox. All right. Are we out of good questions? Are we in dumb question land now? What are the nodes in the MCTS? The nodes are, I showed the action space. So the nodes are like a different, each node is a different way of running basically the same kernel. Wow, if we're really off into the weeds, guys, they're cousins. They don't collude, okay? It's not like Jensen and Lisa Su get together and say, hey, why don't you make your software suck balls so we could be worth $3 trillion and you could be worth 250 billion. And Lisa Su is like, okay, Mr. Jensen. What, you think that's what happens? Come on. They just suck at software. And they don't see any, it's not important to them. It's very clear that it's not important to them, and they'll continue to suck at software, and they'll continue to have 10% of the market share of Nvidia, right? Like, it's not going to change. People think like, oh, AMD is going to get fixed. Like, it's really not. I don't know. I don't want to go into this rabbit hole again. You just need to like what? How many therapists does it take to change a light bulb? One, but the light bulb has to really want to change, right? Where do I work out? Right here in the comma gym. Yeah, let's go. Didn't AMD buy some AI companies? Yes, completely the wrong ones. Guys, they want to lose, okay? Like, some people want to lose. Bug bounty programs? These are the people who ruin security, man. Security used to be like, showing people goat say in the middle of a CTF and like, laughing at noobs, right? Those were the good old days, Well, I heard we're going to make America great again, so, maybe we can make hacking great again, too. I don't even know what the A and the N are, but we're definitely not talking about trains and buses, man. Any plans for using RL to optimize search? Well, if you've watched my channel, you know exactly what I think about RL. AMD is a culture problem, not a manpower problem. That's true. RL is a scam, but not as big. No, RL works someday. Bug bounties, you'll always be a loser if you do bug bounties. Just I love when people what people should really do with 0 days is just drop them on Twitter, right? George, you're influential in the security community. You can't say, oh my God, we got really spicy on the stream. Just drop your 0 days on Twitter, man. Sorry, X. I dropped it on X, man. Respect, right? That's you want to gain respect as a security researcher. Just like, here's a weaponized Chrome 0 day, dropped on Twitter. Don't actually take any of my advice. Everything on the stream is for entertainment purposes only. I take no responsibility if you choose to murder somebody after watching my stream. I do frequently say not to kill people. I think that's a good note to end things on. Isn't RL just MCTS but worse? RL has incredible potential. RL will one day grow up to be something, but today RL does not work. I mean, like, kind of works. I don't know. Remember, press the light up button? Remember getting frustrated by, you almost forgot not to kill people? Well, good. I'm here to remind you. We're back. But don't do bug bounties, man. I got paid $3,000 for this Chrome 0 day that could have brought down the internet. Yeah, great, man. Dreamer v3 works. PPO does not. Yeah, I mean, that's probably the truth. It's probably going to be some like fancy hyperparameter tune thing that kind of works. Like GANs work, but your GAN doesn't work, right? Like style GAN works and Dreamer v3 work, but your GAN and your RL don't work. So yeah, I don't know, but build infrastructure, make it easier. Look at that. Look at that kernel there. Look at that. I found it at 4,432. It just continues to get better. Yuri, thank you for gifting subs. Do you have a last question to ask the stream? Bye.